Hello, everybody. So we are done with quantum mechanics. We are done with uh, crystallography. And there are two more pieces of information remaining to complete the first part of this course, fundamental physics. The first piece of information is about statistical physics. It will take 2 lectures. And the second piece of information is some elements of band theory of solids, the third lecture. Both pieces of information are absolutely vital to understand electrons and holes in a semiconductor. So in today's lecture, I will tell you about the main concepts of statistical physics, microstates, macrostates. I will tell you how chaos leads to new laws, statistical laws of large collections of particles. And I will introduce the postulate of equal a priori probabilities. I will show how this postulate leads to what is called grand canonical distribution. I will tell you what it is. By the way, I will be following the footsteps in this lecture. I will be following the footsteps of Ludwig Boltzmann, a great Austrian physicist who lived in the late 19th century. So finally, I will tell you what we mean by thermodynamic equilibrium. In statistical, in life, we usually deal with a large collection of particles. For example, in a metal, a cubic centimeter of a metal contains about 10 to the power 23rd electrons that are flying around freely. In semiconductors, the number of electrons per cubic centimeter is somewhat lower, like from about 10 to the 10th to about 10 to the, I do not know, 17th, depending on the semiconductor. But it's huge. It's huge. And it is absolutely impossible to describe such systems with 10 to the power 20th or so particles using the laws of motion in classical physics or Schrodinger's equation in quantum mechanical description, simply because there are so many particles. And the very fact that we have so many particles that prevents a direct application of equations of motion or Schrodinger's equation actually becomes our friend. It allows to apply a different type of description based on the laws of probability to uncover some of the regularities in the behavior of these large collections of particles. So let me begin by introducing the concept of a microscopic state, microstate for short. Microstate contains the most complete information about the system. If you are treating the system from the point of view of classical physics, that is Newtonian equations of motion, then you need to specify the coordinates and the velocities or coordinates and momenta of every particle involved. If you are using a more advanced quantum mechanical description, then you need to specify the wave function that depends on this huge number of coordinates, R1, R2, and so forth, Rn, where capital N is the number of particles that you have. Let's say it is 10 to the power 25th, whatever. And the defining property of the microstates is that if you know the microstate at some moment of time, and the system is isolated, it doesn't interact with the rest of the universe, doesn't exchange heat, the rest of the universe doesn't exert any forces on any particle in your system, then you can apply the laws of motion, or you can solve Schrodinger's equation and predict the microstate of the system, that is in classical description, coordinates and momenta. In quantum mechanical description, that would be the wave function. So you can predict the microstate of the system at any future moment of time, in principle. although not in practice. All right, so that's the microscopic state. The one problem with the microstate-based description is, of course, the huge number of particles involved. As I mentioned already, I do not know, 5 times, 10 times. There is another problem with this thing, with this description. It is that unless the system is extremely simple, for example, you can have a simple harmonic oscillator. A simple harmonic oscillator is easily understood. Its behavior is described by sine or cosine of omega t, something like that, where omega is the natural frequency. But if the system is nonlinear, that is, the forces. So in a simple harmonic oscillator is a linear system. If you displace the system from equilibrium, then the force which tries to return it back to equilibrium is proportional to the displacement. Now, in nonlinear systems, this proportionality is lost. It is not there. So this is what we mean by nonlinear. All right, so nonlinear systems exhibit the phenomenon called chaos. And this is what I wrote, how we can define chaos. So chaos is a random, unpredictable behavior which is strongly affected by the smallest change in the initial conditions and or the tiniest external perturbation. Now, I didn't look it up. I didn't look up this definition in any textbook. But this is more or less the same definition which is universally adopted in physics. More or less the same definition of chaos. And chaos is the generic type of motion in all nonlinear systems with a relatively large number of degrees of freedom, like 3 degrees of freedom. You do not really need a huge number of particles. You do not need 10 to the 20th or so number of particles in order to observe chaotic behavior. You can have a reasonably small number of particles too. For example, the first, or maybe one of the first theoretical descriptions of chaos is due to a French mathematician and physicist, Henri Poincaré, who tried to understand the behavior of 3 gravitating bodies. So Isaac Newton solved a 2-body problem, like the sun and a planet, like the Earth orbiting around the sun. And Poincaré wanted to understand how would 3 gravitating bodies behave. And he discovered that actually this behavior, even though it is governed by deterministic Newtonian equations of motion, deterministic in the sense that if you know the initial state of the system, initial coordinates and initial velocities of all 3 planets or stars, the future evolution of this system is strangely irregular, chaotic, random, unpredictable, in spite of the deterministic character of the equations of motion that govern this system. By the way, as an aside, I would like to recommend a very nice, great piece of literature to those who enjoy science fiction. It is the trilogy by a Chinese writer, Liu Cixin, who the book is called The Three-Body Problem, and it is one of the central pieces of this trilogy is a remote planet which finds itself not near 1 star but near 2 stars. So we have 2 stars and the planet, a 3-body system, and how people on that planet felt. All right, so anyway, back to our chaotic motion. So in fact, you do not need a system with 3 planets or 3 gravitating objects consists. Each object performs 3-dimensional motion. So we have 3 times 3, 9 degrees of freedom, 9 coordinates plus 9 velocities, so 9 momenta components, and 9 coordinate components. You do not need that many. Let me show you a movie which demonstrates a chaotic behavior even for a smaller number of degrees of freedom. So here we go. A double pendulum that consists of 2 masses, 1 and 2, connected by rods, rigid rods. And this rod has a pivot point, so it can rotate. This rod can rotate around the first mass. The system is pretty simple. The 2 masses, the rods are of course assumed to have 0 mass. The 2 masses, 1 and 2, I have set their values to, 105, but it doesn't matter what their values are. Okay, let's set them to 2 and 2 equal masses. Well, and there is a gravitational force acting on both. So let's see what happens. Start with some initial conditions and go. Now, if anybody could predict, started to rotate, stopped rotating the shorter rod. See, this is an example of chaotic motion. Simple system, simple Newtonian equations of motion. Force given by a simple expression, mass times acceleration of gravity times sine of the angle or something like that. And yet such a rich and beautifully, crazy, beautifully crazy behavior. All right. All right, the second video has 3 non-interacting double penduli. They start with the same almost the same initial conditions, but those conditions slightly differ. And then see how, this is the middle of the video. Start, go, and see how quickly the trajectories of the 3 penduli diverge from each other. So this is what I mean by the sensitivity to the tiniest change in the initial conditions. And it is clear if the dynamics of the system is so sensitive to a small change in the initial conditions, then it also will be very sensitive to tiniest forces exerted by the outside world. Yeah. All right, so beautiful simulation. By the way, I downloaded this video from Wikipedia page called Chaos. All right. So back to our lecture. The nonlinear systems with more than 1 degrees of freedom are generally chaotic. So there is absolutely no hope to solve the equations of motion exactly on using pencil and paper. You can simulate them on a computer, but the computer simulations will give you chaotic behavior. Furthermore, even if we could solve these equations for an isolated system, the system any system in real life is not perfectly isolated, because there is gravitational field produced by the rest of the universe, the rest of the planets. This alone is sufficient to render the motion of atoms, for example, in a gas, to be completely different than their trajectory in the absence of the universe, if the atoms were isolated. Like you displace somebody in the galaxy Alpha Centauri sneezes, and this has an effect on the molecules in the gas in the air in this room. So, in view of the unpredictable nature of motion of the atoms or electrons in a solid, or atoms in a gas, we cannot rely on solving the equations of motion, Newtonian equations of motion for classical description, Schrödinger's equation for quantum mechanical description. We need another way of describing this system, and it is offered by probability theory. We need a probabilistic description for microscopic states. Once, let's say, we know the probability of occupying a particular microscopic state, what information can we extract from that? We can tell something about the macroscopic states of the state of the system. And by macroscopic state, or macro state for short, I mean a relatively small number of parameters that describe measurable properties such as the energy of the system, the temperature, the pressure, the force the system, let's say the system is a gas, the force it produces per unit surface area. This is the pressure. All right, so that's the idea. That's the strategy. Of course, a microscopic state is a huge collection of all coordinates and momenta, or a wave function of a huge collection of coordinates. We can compress all these labels for coordinates and momenta, for example, into a single variable. Let's call this variable alpha. So we will denote a particular microstate with the Greek letter alpha, and alpha, like as I said, is a huge collection of variables, like, for example, coordinates and momentum. And let us define the probability to find a system in a given microscopic state alpha as P sub alpha. So if you measure somehow, I'm not saying this is easy to do in practice, but in theory, yes, we can fancy that we can measure the microscopic state of the system, and if you perform this measurement, the probability for the system to find itself in the microstate alpha is P sub alpha. And let us say that we are interested in a particular property of the system. Let's denote it with the letter capital Y. For example, this property could be the energy of the system. And in the microscopic state alpha, this property has the value Y sub alpha. Now, if I measure this property Y, this measurement takes a finite time. In fact, our human time is seconds? Well, probably the shortest time unit which we still can distinguish is maybe 1/10 of a second. But from the point of view of atoms, the time it takes for us to measure this property alpha is very, very, very long, because electrons are moving at huge velocities, like 100 kilometers per second, or atoms are moving at the velocities not 100 kilometers per second. Atoms are moving a little bit slower, maybe kilometers per second, maybe 100 meters per second, but it's a huge, the system changes its microscopic state over the time of our measurement by a lot. It visits a lot of microscopic states when we perform this measurement. So this allows us to conclude that what we really are measuring is not the property Y, for example, the energy in a given microscopic state, but the average property Y averaged over many microscopic states. And so the result of our measurement is the weighted average. So you multiply this property y in the microscopic state alpha with the probability for the system to be in this microscopic state. And you take the sum over all microscopic states available to the system. So this is what we really measure. And there is a hidden assumption that in this formula, that the time average is the same as ensemble average. This is the so-called ergodic hypothesis. So when we perform the time averaged measurement over a single system, we should get the same result as when we take a large number of identically prepared systems, and perform an averaging over this large ensemble of identically prepared systems. All right. So the postulate of equal a priori probabilities. This is really a postulate. You can treat it as an extra law of nature, maybe an assumption, reasonable assumption, whatever you like to call it. And it simply says that the system, your system, for example, a gas in a volume, eventually reaches an equilibrium state, no matter how you prepare your system initially. And let's say it is isolated, so it doesn't interact with the rest of the universe. So eventually the system will reach an equilibrium state, and this special state, which we call equilibrium state, is characterized by the fact that all microstate probabilities are the same. Of course, these microstate probabilities must be consistent with the constraints that we impose on the system. So, for example, if the system is isolated, then the volume of the system is fixed, the number of particles in the system is fixed, and the energy of the system is fixed due to the energy conservation. And hopefully, the momentum of the system is zero and the system is not rotating, so the angular momentum is zero. So these are the external constraints. So all microstate probabilities that are consistent, that are consistent with these macroscopic constraints are the same. And this is the postulate of equal a priori probabilities as formulated by Ludwig Boltzmann in the late 19th century. So this postulate is not derived from anything. It is not a theorem. It is really a postulate. We say that it is so, but we do not know why. We cannot reduce it to more general principles. But it is supported by the experimental evidence, and this is a starting point of all statistical mechanics. All right, so now let's say you have a system. So right now I will derive one of the most striking conclusions from this postulate of equal a priori probabilities, the grand canonical distribution. Let me tell you what it is about. Let's say you have a system, like your system is a big, maybe this room in which I am sitting, and filled with air molecules. And those air molecules are flying around randomly. Sometimes they collide with the wall, so they do what the air molecules do. And they focus on a small volume. I select a small region in space inside that room and inside my room, and maybe I can take like a bottle, open it, and air can fly in and out of the bottle. So I call this small volume the system, really. And the rest of the room, I call it the heat bath. And the difference between the system and the heat bath is quantitative, not qualitative. It is simply that the heat bath is much, 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 much bigger than the system. But otherwise, the system and the heat bath have particles. The particles have energy. They move according to some equations of motion, Newtonian equations of motion, let's say, classically. And they can exchange, the system and the heat bath can exchange particles, and they can exchange energy without exchanging particles. In other words, they can exchange heat. Now, the quantitative difference between the system and the heat bath is this. The heat bath is huge. If you have, let's say, 10 to the power 30 molecules and you add a million, then it is not a big change from the point of view of the heat bath. But if the system has not 10 to the 30th, but 10 to the 7th, 10 million molecules, and you add a million, then it's a noticeable change. It is a change by 10%. So what is small from the point of view of the heat bath is big from the point of view of the system. Now, of course, because of the exchange of particles and energy with the heat bath, the number of particles in the system, as well as the energy of the system, constantly changes randomly. They fluctuate around some mean value. At some moments of time, let's say I would like to look at the system at special moments of time, when the system has a given number of particles and has a given value of energy. So every now and then, in the course of these fluctuations, the number of particles and the energy in the system will have a specific value, and I will just make the snapshots of the system at these specific moments of time. The microscopic states of the system, in all those snapshots, even though the energy and the number of particles and in all those special moments of time are the same, the microscopic states of the system will be different. And, however, according to the principle, the postulate of equal a priori probabilities, the probability of a specific microscopic state of the system will be, which is consistent with a given number of particles and the given energy, will be the same. Okay? So if you have a number of particles n and the energy E, then the probability of the microscopic state alpha will be the same as long as the number of particles and the energy of the system is the same. What does it mean? From the point of view of the probability as a function of the number of particles, what does it mean from the point of view of the microstates of the system, microstates probability of the system? It means that the microstate probability of the system should depend on the number of particles in the system corresponding to this microstate, on the energy of this microstate, and as far as the system goes, on nothing else. This probability may also depend on the properties of the heat bath. So it is some general, so the probability to find the system in the microstate alpha depends only on the number of particles corresponding to that microstate and the energy corresponding to that microstate, and possibly on the properties of the heat bath with which the system exchanges particles and energy in the form of heat. All right. So now let's make things a little bit more complicated. So we have established, this follows from the postulate of equal a priori probabilities. And let's call this function of the number of particles and the energy that gives, this function gives you the probability of a microstate. Let's call it the microstate probability function. And let's denote it with the letter G. So the microstate probability P of P sub n alpha, probability of the microstate alpha, with n particles, is this microstate probability function G that depends on n, the number of particles, and the energy. All right, okay, so now let's make things a little bit more complicated. Let's say that inside this room, inside this heat bath, I have one system here and the other system here somewhere, so that they do not interact directly. The two systems do not interact directly with each other. And I ask myself, what is the probability to find the system number 1 in the microstate alpha 1 and the probability to find the system number 2 in the microstate alpha 2? Since the systems do not interact with each other, they are not correlated with each other, this combined probability will simply be the product of the microstate alpha 1 probability for the first system times the alpha 2 microstate probability for the second system. So in terms of these probability functions, it is G of n1 E sub n1 alpha 1. So this is the probability, microstate probability for the first system, let's say this one. And this is the microstate probability for the second system, and both microstate probabilities depend on the number of particles and energy in the system that finds itself in a particular microstate. On the other hand, we can regard system number 1 and system number 2 as a combined system. And the microstate probability of this combined system will be given by the same function, capital G, general function. I guess I chose the letter G for general. But now the arguments of this function will be the sum of particles, the total number of particles in two systems, that is n1 plus n2. And the energy argument will be the sum of energies in the two systems, E1 plus E2. And from this, we conclude that this probability function has the property which we call multiplicativity. The value of the function, for whose arguments is a sum of two values, G of n1 plus n2, E1 plus E2, is the product of these functions for G of n1 E1 times G of n2 E2. So this is based on the postulate of equal a priori probability. We have established that this function must have this property. There is only one function which enjoys this property. It is a number not equal to 1, not equal to 0, any number. For example, 2 or 10 or any number raised to the power, which is a linear combination of the number of particles n and the energy E. And let's call this the coefficients in this linear combination A and B. And let's choose the exponential to be that number, E 2.718 the base of the natural logarithm, to be that number. Somewhat arbitrary, any other number would do as long as it is neither 0 nor 1, but so we, following the general convention, we will use the exponential function. So exponential to the power an plus be, these parameters a and b should depend on the properties of the heat bath, but not on the properties of the system, which finds itself in contact with the heat bath. Then we have another parameter 1 over z that multiplies the exponential. This parameter 1 over z is the normalization constant. It is there to reflect, to make sure that the total probability is 1. So if we add up all the microstate probabilities for the system, we should get 1, because the combined, the net probability is always 1. And in order to make sure that the probability adds up to 1, the sum of microstate probabilities over microstate adds up to 1, the normalization constant, z, should be the sum of the number of particles in the system, the sum of the microstates, and what is summed. And we are summing over these exponentials. The letter Z comes from the German word Zustandssumme, which means sum over states. Beautiful German word. All right, now let us just rename these parameters, A and B. These are just temporary names, not conventional names, but temporary names, A and B, in the probability function. The conventional name is to use the, instead of B, the letter, instead of the parameter B, they're using the something which is -1 over kt. So B is -1 over kt. It's just renaming the parameters. And instead of the parameter A, I will be using mu divided by kt. I'm just renaming these parameters. Now, the parameter kt and the parameter mu have the dimension of energy. And they have special names. So kt is called the thermal energy. And the parameter mu is called the chemical potential. Their values of the thermal energy and the chemical potential depend on the properties of the heat bath. If you cannot follow the total, perform the measurement over the whole heat bath, so maybe the heat bath is the ocean and you are looking at the state of water in the bottle that you insert in the ocean, right, for example. You can measure the chemical potential and the temperature by measuring the average energy and the average number of particles in the system, because by the definition of averages, the average energy is the sum over the microstates and the number of particles in the system. Energy in a particular microstate corresponding to a given number of particles in the system times the probability of having this microstate and this number of particles. The average number of particles in the system is given by a similar formula. So you have two expressions which contains two parameters, mu and kt. So you can use these two expressions to determine mu and kt by measuring average E and average N. So now, of course, these triangular brackets indicate statistical averaging. All right, now let me tell you about thermodynamic equilibrium. Is it the last slide? Yes, it is. Let's go back to the air in this room where I'm seated. Let's say here we have one system, here we have another system, and by system I mean maybe a little bottle with which is open but which is empty. It is filled with air. And these two systems may exchange energy and air molecules with the rest of the room. On average, the two systems will contain the same number of air molecules, like the two bottles are identical. On average, they contain the same number of molecules, and they have the same average energy here and there. Both bottles have the same number of molecules and the same energy. But the average number of molecules and the average energy depend on the chemical potential and the thermal energy of the heat bath. The air in the room is the heat bath. This means that the thermal energy and the chemical potential at the position of one bottle is the same as the thermal energy and the chemical potential at the position of the other bottle. The thermal energy, and this is what we mean by thermodynamic equilibrium. Thermal energy and the chemical potential are uniform everywhere, have the same value. Now, thermal energy has been denoted as KT. Here, T is actually the temperature, the usual temperature that you measure with a thermometer. And well, even though the thermometer can give you the value in degrees Celsius or degrees Fahrenheit, depending on where you are, the conventional unit of temperature in physics is kelvins. We prefer to use kelvins to measure temperature. 1 degree Kelvin corresponds to 1 degree Celsius. But 0 kelvins correspond to absolute zero temperature. It is negative 272 degrees Celsius, minus 272.15, if my memory is correct. Or is it minus 273? Minus 273. The constant that multiplies the temperature is called the Boltzmann's constant. And it has the value 1.38, 10 to the negative 23rd joule per Kelvin. All right, so that's all for today. Thank you all very much for your kind attention. I'll see you in the next lecture.